Hi, I'm Mike Crowley, and today at Fluid Mechanics I'm going to explain water hammer in pipes. Water hammer is a special transient flow case. Transient flow and the study of transient flow, which is called surge analysis, is concerned with dynamically changing flow velocities in pipe. Water hammer occurs when there is a sudden or rapid change in the flow velocity. It's usually associated with a valve slamming closed or rapid closing of a valve. It can lead to very high pressure transients, which can cause the pipe to fail. Often it is associated with a banging noise, which leads to the term water hammer. Basically, you have a long column of water, and you're rapidly stopping it. It bangs against the valve, and it causes a banging noise. In this lesson, I will explain the theory behind water hammer. I'll show you how to calculate the pressure transients that are induced due to water hammer. I will explain this shortly at Fluid Mechanics. So let me explain what is happening and how to calculate the induced pressures. So if I draw a sketch of a tank connected to a pipe, so this is a header tank with a pipeline connected to it, and in this tank we have a head of fluid, and that is pushing the fluid along the pipe, and it's going to have an initial velocity ui, and it's going into a open tank at this end here. So this is our initial conditions: constant velocity ui initial along the pipe into a tank, and there's a head of fluid which is pushing the flow along. The pressure at the inlet to the pipe is, well, if you've got a head there, it's the pressure equals pressure at the inlet, or pressure initial, equals rho, which is the density, gravity, times the h, the head. Now, knowing the pressure at the inlet to the pipe, and if you know the other conditions along the pipe, you know the length of the pipe, the diameter of the pipe, the viscosity of the fluid, it's possible to calculate what the flow rate is along the pipe. Now, in this video, I'm not going to explain how to do that, but it's not a very difficult job to actually calculate the velocity along the pipe. So then what happens? Well, we show a sudden close. So in the water hammer case, we have a sudden closure of a valve at the end of the pipe. So at some instance in time, the end of the pipe is closed off. And so I'm just going to show a blockage on the end of the pipe there to show that the flow the pipe is being closed. Now, in the instantaneous you do that, you've still got flow coming in at the start of the pipe, but at this end of the pipe here, the flow has stopped because it's got nowhere to go. So what actually happens is it sets up a pressure front or a wave front which travels up the pipe, and I'm going to show it at this position here. And this pressure or wave front travels up the pipe at velocity c, and c is the velocity, the sonic velocity in the pipe. So on this side of the wave front here, the velocity, and I'll put it u, equals 0, and on this side of the pipe the velocity is still the initial velocity. Now, that is a little bit theoretical because that's sort of assuming you had an instantaneous closure of the valve, but no matter how fast you close it, there will be some time it takes you to close the valve. And in that case, what happens, instead of just being a one plane in the pipe, the change in velocity will occur over a section of pipe. So this is probably a bit more realistic, and basically what we're saying is that over this length here, there will be a pressure change, delta P, okay, where on this side the velocity is u, the initial velocity, and on this side of the wavefront the velocity is the zero velocity. So the velocity will be changing across this wavefront. Now the length of this wavefront from here to here is to do with how long it takes to close the valve. So if the valve was closed instantaneously, it would just be a plane, but if it takes a fraction of a second, basically it's how far that wavefront travels in the time. So basically the time it takes to close the valve times the sonic velocity will determine what the length of that wavefront is. Now across the wavefront, okay, the velocity is going from the initial velocity down to zero velocity. There's a change in momentum or change in velocity across that wavefront. That wavefront can only change momentum, or the velocity can only change if there's a force applied to the fluid. Okay, we've now got to look at Newton's second law to work out what the forces applied to the fluid as it goes across that wavefront are. Newton's second law is force equals mass times acceleration. Now in our case we're not talking about forces, we're talking about pressures, and we're not talking about mass and acceleration, we're talking about changes in momentum. So for us, the force that's acting across that wavefront there is the differential pressure dP across the wavefront acting on the area of the pipe. So I'll put down A for the area of the pipe. So now we need to look at, well, what is the momentum change across that wavefront? Well, the wavefront is travelling up the pipe at velocity c. So at any instance in time, we can actually work out how much fluid is travelling through that wavefront, okay? And the amount of fluid that's travelling through that wavefront is basically how fast it's going up the pipe times the area of the wavefront times the density of the fluid. So the mass flow rate part of it is the velocity of the wavefront, c, times the area of the pipe, A, okay, times the density of the fluid, rho. Okay, so basically the momentum, the fluid that's actually going through that wavefront in terms of kilograms per second going up through the wavefront is CAP. So in other words, the velocity of the wavefront, that's the sonic velocity of the wavefront, the area of the pipe, and the density of the fluid. Okay, and that's the mass flow rate going through that wavefront. And how much is the velocity changing? Well, it's going from UI down to zero. So in other words, it's going from the initial velocity down to zero. So the momentum change is UI. So we can take out A from both sides of that equation there. So we've basically got delta P equals C rho UI. Or more generally, we say that the pressure for a sudden closure of a valve is C rho U. Okay, now that equation there is called the Joukowski equation, and it's a famous equation, and that determines what the maximum pressure rise you can get due to water hammer is. So basically the maximum pressure rise is the sonic velocity, the speed of sound in the fluid, the density of the fluid, times the change in speed of the fluid. So it's the initial speed going down to zero. So let's try and apply this equation to, say, a 15mm copper pipe. And say if we had a 15mm copper pipe with an initial speed of 1 meter per second. And what we want to do is find out when we suddenly close the valve how much pressure rise we're going to get for a 15mm copper pipe. Well, let's just put down some details first of all of the copper pipe. So we've got a diameter of the copper pipe is 15mm, and the initial velocity U equals 1. Okay, 1 meter per second. That's 15 millimeters. 1 meter per second in a 15 millimeter pipe is actually equivalent to 8.7 liters per minute. Okay, so when we look at this equation and we try to apply it, well, the first thing we can say is, well, if we were talking about water in a copper pipe, that's what I'm talking about here. We know the initial velocity, that's going to be 1. We know the density of water, that's normally 1,000 kilograms per meter cubed. The thing we're not sure about is, well, what's the sonic velocity? And that's what I'm going to talk about next. So to find the sonic velocity in a fluid, well, you need to apply Hooke's law to the thing. Now if we assume that the pipe is perfectly rigid and does not flex, okay, you can apply this equation, which is Hooke's law, which basically says that the sonic speed is equal to the square root of the bulk modulus, okay, divided by the density of the fluid. Now, for water, let's just calculate that out. For water, we got C equals the square root of the bulk modulus of water is 2.19 times 10 to the 9 pascals, and the density is 1,000. So if you calculate that, you get a speed of 1,480 meters per second. Now that's assuming that the pipe is perfectly rigid, but pipes aren't perfectly rigid, they actually flex, and that actually affects the stiffness of the system, and as it gets less stiff, the sonic speed comes down. So there's a modification you can do to this equation to take into account the stiffness of the pipe, and basically you modify Hooke's law, the equation, so that C equals the square root of 1 on, let's just think about this, rho 1 on K plus D on So what's this equation saying? Basically what this equation is saying here is that the sonic speed is the density, same as there, 1 on K, that's the bulk modulus, plus D. D is the diameter of the pipe, E is the Young's modulus of the pipe material, and then little e is the wall thickness. Okay, so this is now taking it, this term of this part of the equation here is taking into account the stiffness of the actual pipe itself. If the pipe was perfectly rigid, then effectively what that's saying is that you have infinite Young's modulus for the material, and if that number was infinitely large, then this term would drop down to 0. Okay, and if that's 0, if you put 0 in there, you'll effectively come back to this original equation here. So basically that's how it's modified. So as this becomes less stiff, then this term in the equation becomes more important, and it actually reduces the speed. So if we actually now put in some numbers for that, now for a copper pipe, E of the 15 for a standard 15mm copper pipe, I believe the wall thickness is 0.7 millimeters, and for copper, E Young's modulus is 120 times 10 to the 9 pascals. Okay, so if I put those numbers into that equation, if I put those numbers into the equation, we'll get times 10 to the 9. Okay, and if you work that out, you get C equals 1,254 meters per second. So the velocity has come down from, for a copper pipe, from 1,480 for a perfectly rigid copper pipe down to 1,254 meters per second. Actually, copper pipe is very stiff, but it all depends on the pipe you're choosing. So if you're talking about the pipes that take water to your house, the plastic pipes that they nowadays use in the road, typically you'd find the wave speed in one of those would be around about 1,000 meters per second. But if you took a very flexible pipe, like say a garden hose pipe, you know, you could be talking in terms of hundreds of meters per second. The other thing to bear in mind about the wave speed, though, is the bulk modulus. Water, in particular, is very stiff. Okay, so that's 2.19 times 10 to the 9. Now, that's true as long as there's no air in the water, but often you get little small air bubbles in the water, and they can have quite a significant effect on the bulk modulus and bring down the speed quite significantly. So that can be quite an important factor. But anyway, we'll carry on with the calculation. So we now want to work out what the pressure rise is due to this closure of this 15 millimeter pipe with a 1 meter per second flow in it, and we close the end of the valve. Basically, the pressure rise then equals, so we just apply, we have the numbers now to apply to the Joukowsky equation. So the pressure rise, looking at the Joukowsky equation, is going to be C, which is 1,254, times the density of water, which is normally 1,000 meters per 1,000 kilograms per meter cubed, times the velocity, which in our particular example is 1. And if we work that out, that comes out at 12.54 times 10 to the, and I'm going to put it in times 10 to the 5, because 1 times 10 to the 5 is 1 bar. Okay, so that's basically equals 12.5 bar. So that's the pressure rise you would get in that particular case, maximum. I happen to know that the pressure rating of a copper pipe, I believe of that specification, is 58 bar. So the safety factor for that particular case is 58 bar divided by 12.5, which equals 4.64. So the safety factor is 4.64. Another way of looking at that is, well, if we'd actually had a much higher velocity, so in other words, if the initial velocity was 4.64, we would have actually then got 58 bar. Now, for a copper pipe, that will be going some. So actually, normally for copper pipes, when you close the end of the valve, you don't have a problem from a burst point of view. But just be a little bit careful with that, because the burst pressure is not the only thing that's important when you're designing a hydraulic system. You've got all the fittings on the end of the pipes. They're quite highly likely to be ripped off if you go excessive pressures. You've got all the bracketry on the walls and things like that. If you've got movement in the pipes, you might affect that. And obviously, if you've got bends in pipes, they can tend to flex. So there are other things to take into account. So in summary, to calculate the pressure rise due to a sudden closure and water hammer, what you need to know is the initial flow conditions and the initial flow velocity. You need to understand or work out what the sonic speed is, and I've shown you in the lesson how to calculate that. And you need to know the density of the pipe, the density of the fluid. From that, you can apply the Joukowsky equation, and basically the maximum pressure rise is the product of the velocity, the wave speed, and the density. If you have any questions on this, then please leave a comment on my website blog, and I will endeavour to answer any questions there. I cannot answer any general questions directly by email, but I will, if you leave a question on the blog, try and answer it there. If you need any more detailed advice, particularly if you need advice on surge analysis on a sort of consultancy type basis, well then please contact me directly. That's it today from Fluid Mechanics. Thank you for listening.